everybody to this talk organized by BİRİCİKBİLİM. Today we have Professor Kinney from University at Buffalo, who's going to give a talk about cosmic inflation. So Professor Kinney, please go ahead.
Okay, thanks for inviting me. I'm excited to give you guys a sort of a summary of inflationary cosmology. This is not going to be a hugely technical talk. I'm trying to avoid a lot of mathematical detail and stick mostly to the conceptual ideas, although there'll be a little bit of math involved. But a lot of this can be understood in mostly geometric terms, if nothing else. So inflation, basically speaking, is a theory of what happened before the Big Bang, or at least before the hot thermal equilibrium initial state that we usually attribute to being the Big Bang. We'll make a distinction later on between the initial singularity and this hot early universe, but for the moment, that's not terribly important. So in order to lead up to this, let's talk about the origin of the universe itself, right? The physics of the standard Big Bang cosmology, what its problems are, and how inflation addresses those problems and creates a larger picture in which the Big Bang universe is embedded. So we'll start by looking at special relativity, right? So this is probably familiar to most of you who are physics students. This is the length element in Minkowski space in special relativity. That is that, let me bring up an annotation here. So this is essentially the proper time along a path in space-time. This is the four-dimensional space-time equivalent of a length. That is, along a path through space and time, an observer sees a time pass ds that is given by this expression here, which is just dt squared minus dx squared, right? So this is the standard Minkowski line. This is the standard Minkowski line element, and it determines a causal structure for space-time. And in particular, we know that in special relativity, objects travel, and this is normalized to the speed of light being equal to 1. So we're measuring time in seconds and distances in light seconds, or time in years and distances in light years. In those units, the speed of light is equal to 1, and the path of a photon, the length through space-time that a photon travels, is dt squared is equal to dx squared, so that ds squared is equal to 0. Okay, so photons travel on paths of 0 length in space-time. So we can draw a diagram of space-time that looks like this. So we have, what I've done here is simply suppressed one dimension of space. So instead of a 3 + 1 dimensional, 3 dimensions of space and 1 of time, in here I have 2 dimensions of space on the horizontal and 1 of time on the vertical. And any point in space and time, any particular spot in this 4-dimensional manifold, is referred to as an event, and I'll just label that with a label P. That is, this is something that happens. Any event that happens in space and time is. I am no longer sharing my screen. Why did that happen? There we go. Back to screen share. Good. For example, a supernova going off, or your birthday, or any particular thing that happens in space and time is referred to as an event. And space-time is just a collection of events structured according to with a particular causal structure. And so if I want to, for example, imagine that a supernova goes off at this particular point in space, particular point in time, light will travel out in a spherical wavefront from that supernova, traveling outward at the speed of light. So what you will see is, as you move forward in time, that spherical wavefront is going to, and in this case, it looks, let me get my annotation back up again. So in our restricted space, in our 2-dimensional universe, this wavefront looks like a circle that's expanding with, why does that keep on sharing? Expanding with time. So as we go forward in time, that wavefront gets larger and larger and larger. So we see as we move forward in time that this expanding spherical wavefront moving out from this event where it was originally emitted, sweeps out in space-time, sweeps out a cone, right? So the edge of this cone is the path of a photon, which goes at 1 light year per year, is a 45-degree angle on this diagram. All light rays travel at 45-degree angles, and the causal future of any event, anything that it lies is causally connected into the future from this event, lies inside this light cone. This should all be relatively familiar to you. So for example, if I start at this event, for example, this supernova going off or a flash bulb or anything that emits a pulse of light, if I travel at exactly the speed of light, I will travel out along this 45-degree line on the light cone. If I travel at less than the speed of light, I will be inside the light cone, but to reach any point outside this light cone, starting at this event P, I have to have a velocity that's greater than the speed of light. I have to travel at faster than 1 light year per year, for example. So this creates a causal structure for my space-time that I can draw like this. And in particular, there's also a past light cone that is defined by photons incoming on that event P. And so I can define a causal future of any event in my space-time as being this future light cone, and I can define the causal past of any event in my space-time by this past light cone. Everywhere else is inaccessible fundamentally from this. If I start at this point in space and time, all of these other points that are inaccessible that would require me to travel faster than the speed of light, I label elsewhere, and they're causally disconnected. They can have no causal influence on what happens at this event P, nor can they be causally influenced by this event P. So they're completely causally disconnected. So causal future lies inside the future light cone, and causal past lies inside the past light cone. Now notice in special relativity, which is what all we're talking about so far, is that both these future and past light cones extend infinitely, right? The Minkowski space is a complete manifold. It extends infinitely into the past, and it extends infinitely into the future as well. How do we adapt this to an expanding universe? How do we describe a cosmological space-time? If we want to have expansion, something dynamics applied to the space-time, but still preserving the cosmological principle, the idea that the universe is homogeneous and isotropic, the way we generalize this Minkowski metric to an expanding space-time is we add a time-dependent factor, this a squared of t, that, let me see, so let's try doing this. So now what we do is we add a time-dependent scale factor to the spatial components of our metric. That is, spatial distances are changing with time as we move either forward or backward in time. And so this is how we describe an expanding universe. In particular, if the scale factor is a of t is growing with time, that describes an expanding universe. Okay. So we can, for example, draw a geometry that's equivalent to a flat universe by drawing a grid of squares on a flat two-dimensional surface. So this is a two-dimensional analog of a real three-dimensional universe. And one of the big misconceptions that I think a lot of people have, even some fairly technically sophisticated people, is this idea that the Big Bang or the beginning of the universe happened at a particular point, that it was like a cosmic egg, so an explosion that happened at a particular point with everything flying outward in space from that center of expansion. That's absolutely not the way it works. That's completely wrong. Because of the cosmological principle, the idea that the universe is homogeneous and isotropic, the universe can have no center and no edge. There is no special position in the universe. Homogeneity is the idea that the universe is the same at every point. Isotropy is the idea that the universe is the same in every direction. And the basic assumption of cosmology is that the universe is homogeneous and isotropic. This is also well supported by data, as we'll see later. So a better way to imagine the expansion of the universe is to imagine drawing just a grid of squares, or if you want to generalize this to 3 dimensions, it would be a space full of cubes, right, divided up into identical cubes. Everywhere on this grid of squares, every square on this grid is identical to every other square. There's no special place on this. It satisfies the constraint of homogeneity, but it only satisfies the constraint of homogeneity if it has no edge, which means it must extend infinitely in all directions. So imagine taking a flexible sheet of rubber or something like that and drawing a grid of squares on that sheet of rubber. And then furthermore, imagine that sheet of rubber going off infinitely in all directions. So expansion then on this infinite grid of squares consists of all of the squares growing larger with time. So as that scale factor increases, the spatial distances between objects on that manifold increases, and so these squares get bigger and bigger and bigger with time. And notice, however, that at any point in time, all of the squares are identical to all of the other squares. Furthermore, the grid extends infinitely in every direction at any given time, and therefore the space is completely homogeneous. There's no special point in the universe. Every point is exactly the same as every other point. And if, for example, if we are sitting at rest with respect to a square at the center of the grid, so if this is where we're living right here, then what we see is everything moving away from us with time, right? So if we put ourselves here, as the universe expands, what we see is all of the other points, all of the other galaxies, for example, would be fixed with respect to the points on this grid. They would all be moving away from us faster and faster. And furthermore, they would be moving away from us faster the further away they are, right? So in fact, it's not hard to convince yourself that this would replicate the idea of a Hubble law, where the rate of recession of an object is proportional to its distance. So something that's closer to us will be moving away from us more slowly. Something that's further away from us will be moving away from us more quickly. So this is a better analogy for the expansion of the universe, is this infinite grid of squares where all the squares are identical to each other, but they're all growing larger and larger with time. And cosmic objects, galaxies, for example, things that are at rest relative to the cosmic expansion, are then at rest relative to this grid, and everything is moving away from everything else. Everyone sees themselves at rest at the center of the expansion, and everything else in the universe moving away from them. And it doesn't matter where you are, you will see exactly the same thing. So this is a more accurate picture of cosmological expansion. So now imagine that we turn the clock backwards. We go backward in time. What happens if we extrapolate, say, what's the history of this, right? So if we plug this into the Einstein field equations that I'll show you in a minute, and run the clock backwards, what we find is these squares get smaller and smaller and smaller, and eventually these squares will, if we go far enough into the past, these squares will collapse to zero size. And this is the initial singularity of the Big Bang, right? So in a standard Big Bang cosmology, if we solve the equations of motion for this expanding infinite grid of squares, we extrapolate that backward in time, what we find is that at finite time in the past, all of those squares go to zero size and the space-time becomes singular. This initial singularity is referred to as the moment of the Big Bang, okay? And that happens, the important point is that that happens finite time in the past. Notice also that the universe never asymptotes to zero size, even at the moment of the Big Bang. As we go further and further into the past, the universe at any time in the past is always spatially infinite. The squares are getting smaller, but the overall size of the universe is always infinite, all the way back to the moment of the Big Bang itself. So the Big Bang doesn't happen at any particular center of expansion. The Big Bang happens everywhere in an infinite space at once. So a more accurate way to think of the Big Bang is that an infinite, geometrically flat, homogeneous universe springs into existence all at a single time. And the Big Bang then is not a boundary in space, it's not a position in space, it's not a place, it's a boundary in time at which an infinite universe springs into being, homogeneous, isotropic, all at once. We can draw this on a space-time diagram by using a trick. We can rewrite this Robertson-Walker metric with the expansion factor by pulling this expansion factor out in front as an overall conformal factor in our metric. And then by measuring time with a clock that slows down with expansion. This is called conformal time, and I'm going to use the symbol tau for that. And so if we measure time in conformal time, the special clock that slows down with the expansion of the universe in space in what are called co-moving coordinates with respect to this expanding grid, then the scale factor just becomes this overall conformal factor, and it keeps kicking me out of this. There we go. This a squared of t then is an overall conformal factor that just tells you the amount of expansion. The point here is that photons still travel on units of zero proper time. So that means that we can draw space-time diagrams in conformal time exactly as we would in Minkowski time with the conformal d tau is equal to dx, right? So on a conformal diagram of a Robertson-Walker space, light cones are still at 45 degrees, and the causal structure looks exactly like the causal structure of Minkowski space, with one difference. Minkowski space, remember, both the forward and the past light cones were infinite in extent. Time extends infinitely far into the past and infinitely far into the future. But in a Robertson-Walker space, time extends infinitely far into the future, but not infinitely far into the past. In fact, that there is this moment of a singularity, which is the Big Bang. So if we draw our past light cone in a cosmological space-time, so we're up here, this is here and now. If we look back along our past light cone, looking out in space is looking back in time because of the finite speed of light. If we look out at something if we look at the sun, we see it as it was 8 minutes ago. If we look at the Andromeda galaxy, we see it as it was 2.5 million years ago. If we look at a supernova at a distance of 1 billion light years, we see it as it was 1 billion years ago. So we look out along our light cone, we look out in space, back in time, and if we look further and further out in space, we see further and further back in time, and if we look far enough out in space, we actually see far enough back in time that we actually see the Big Bang itself. So if we can make a telescope that can see out, so the age of the universe is known to be 13.8 billion years, plus or minus about 200 million. So if we can make a telescope that can look out 13.8 billion light years, or because of expansion effects, it's a little bigger than that, closer to about 40 billion light years, then we would actually see the Big Bang itself. And so the Big Bang, once again, is not a position in space, it's a moment in time. It's a boundary on this space and time, and what it does is this surface of the initial singularity chops off this past light cone at some finite past time. And before that, nothing exists. There is neither space nor time. So the causal structure of a Robertson-Walker space, or a flat Robertson-Walker space at least, is identical to a Minkowski space, except with the past light cone chopped off at the moment of the initial singularity. And this is the idea of the Big Bang spacetime. Our past light cone is finite, and we can only see out a finite distance in the universe because the universe has a finite age. And we'll talk about that in a minute when we talk about horizons. So how does this work dynamically? Depends on what's in the universe, right? So the equation of motion for a flat Robertson-Walker space is that the expansion rate, which is given by the Hubble parameter, let's try annotating again and see if I don't get kicked out. So the Hubble parameter, which is just given by the logarithmic derivative of the scale factor with respect to time, is I equal to A dot over A. The equation of motion, Einstein's field equation for general relativity applied to this homogeneous and isotropic space, tells you that the square of the Hubble parameter is proportional to the energy density of the universe. And furthermore, you have a second equation, which is a continuity equation, which tells you how the energy density varies with expansion, right? So in the first equation is John Archibald Wheeler's famous statement that matter tells space how to curve. That's the first equation. The energy density tells you the expansion rate of the universe. And the second one is space tells matter how to move, or in this case, in the continuity equation, that the expansion tells you the time dependence of the energy density. And these two equations together form a set of nonlinear ordinary differential equations that can be solved for the time evolution of the universe, okay? And in particular, the details of the time evolution depend on the equation of state of the stuff that is in the universe. It depends on the energy density and the pressure, or more specifically, how the energy density scales with expansion itself. And so there are three basic categories of stuff that we can put in the universe that all behave differently, that all affect the expansion differently. The first and simplest category of stuff is called matter. The idea here is, imagine that I have a box that is co-moving with expansion, that is, it's expanding along with this, the expansion of the universe, and I fill it full of a dust of particles, hydrogen atoms or dark, any sort of basic, just a massive, a bunch of massive particles that I approximate as being non-interacting. Well, then I find that the energy density, or the mass density, which is just the same thing, right? So that mass is energy, that the energy density of the material inside that box scales as the inverse of the volume of the box. As the box gets bigger, the energy density decreases because the matter inside of it is diluted proportional to the volume of the box. So the energy density goes as 1 over the scale factor cubed, which is a factor of 1 over the volume of this box. If I take that and plug this into the Einstein field equation, this tells me that, in fact, the equation of state for this stuff is going to have a pressure of 0. It's non-interacting. And that I can solve the continuity equation for the energy density in this way. And then I can solve the Einstein field equation for the Hubble parameter. And what I find here is that the scale factor evolves as time to the 2/3 power. And this gives you a nice example of how this is past finite. At time 0, that scale factor goes to 0, and I have an initial singularity. The second type of material that the component to my universe that I can pick is generically called radiation. And this is any species that is relativistic, where the momentum of the particle is much, much larger than the mass. So this would apply to photons, for example, neutrinos up until very recently in the evolution of the universe, any massless species has two effects that happen. One is that the number density, imagine a box full of photons, for example. The number density of those photons is going to drop as 1 over the volume of my box once again. So that gives me an energy density that scales as 1 over the scale factor cubed. But there's an additional factor there because these photons are also going to redshift with expansion. So the wavelength of the photon stretches proportional to the scale factor, which means the energy per photon drops proportional to the scale factor, which gives me an extra factor of 1 over A. So the energy density of radiation, because of cosmic redshift, instead of scaling as 1 over A cubed, scales as 1 over A to the 4th. And I can plug this into the Einstein field equation in a similar way, and what I get is the scale factor evolves as the square root of time rather than t to the 2/3 as in the case of a matter-dominated universe. But still, as t goes to 0, I have the scale factor goes to 0, and I have a singularity. The third kind of matter that we're going to care about, or the third kind of component of this cosmic cocktail for the universe, is vacuum, energy of empty space itself. So this is also referred to as a cosmological constant. The idea being here, if I assign energy density to empty space itself, if that energy density is constant, then as the box expands, the energy density in the box doesn't change. The total energy in the box goes up with expansion. This actually violates conservation of energy quite trivially, right? So if the energy density in this box is constant, as the box grows, the total amount of energy in the box grows with time. So vacuum-dominated expansion violates conservation of energy, which is okay in general relativity. You can do that globally as long as you don't do it locally. And what you find if you have a constant energy density is that the scale factor now behaves exponentially. The scale factor goes as an exponential in time, where the time constant of that exponential is just equal to is given by the square root of the energy density, or is given by the Hubble parameter. So these are the three basic types of components of the universe. And our real universe, of course, consists of a mix of all three of these things. And it turns out that in the present universe, it's vacuum energy that dominates. So 73% of the energy density of the universe is in something that behaves a lot like the energy density of empty space. This vacuum energy that violates conservation of energy that currently in the universe makes up about 73% of the energy density. The rest of the energy density is made up of 23% cold dark matter, and as yet unidentified, presumably some sort of new species of particle, although we don't know that for sure. And about 4% of the energy density is in material we understand, as in ordinary atoms, baryonic matter, hydrogen, helium, photons, neutrinos, all that stuff, right? Although the relativistic degrees of freedom, the radiation part, is mostly cosmic microwave background and neutrinos. That only makes up about a factor of 10 to the -4 in this pi. It's not even visible on this chart. However, so matter and dark energy win by energy density in the current universe. But radiation, photons, and neutrinos are a win by number. They're far more numerous than the number of atoms in the universe. So as we go back in time, we remember that the matter density scales as 1 over A cubed. the radiation density scales as 1 over 8 to the 4th. So if we run that backwards in time, the radiation becomes more and more important, and eventually the early universe will have been dominated by radiation, and the current, then it would have gone through a phase transition to a matter-dominated phase, and then finally another transition to the current phase that we're going through now, which is dominated by dark energy. So here's a basic layout of the history of the universe. In a standard Big Bang cosmology, we're going to modify this when we talk about inflation, is that the early universe would have been radiation dominated. And as we go back in time, because everything's getting squashed together, everything's also getting hotter, right? If I take a gas of baryons and photons and compress it, the temperature is going to go up. So as I go back in time, I go up in temperature. So if I start today at a temperature of 3 Kelvin, it turns out that the universe ceased to be matter dominated, became vacuum dominated when it was about 1 billion years older at a temperature of about 5 Kelvin. There was a phase of matter domination from starting about 60,000 years after the Big Bang up to about 1 billion years. The universe was dominated primarily by dark matter. Going further back in time, earlier than the epoch of matter radiation equality, earlier than about 60,000 years after the Big Bang, the universe would have been dominated by the radiation degrees of freedom, photons, neutrinos, and then other species of particles as their temperature increased above their masses. And we have this basic timeline with a lot of gaps in it as to the history of the universe. So at a temperature of 10 to the 32 Kelvin, whatever was going on would have been described by quantum gravity. This is the Planck temperature, above which we would need a theory of quantum gravity to explain it. At about 10 to the 26 Kelvin would have been the epoch where presumably the strong force and the electroweak force would unify into a single force. We don't know for sure that that happened, but it's reasonable to guess that it did. That would have happened at a temperature of about 10 to the 26 Kelvin, which is also, roughly speaking, where we expect inflation to have happened. So we're going to take everything earlier than this point at grand unification, and we're going to replace it with a new model in a minute. After that, not much is known. Down to a temperature of around 10 to the 16 Kelvin, which is the highest energy that we can probe. So this is the electroweak phase transition would have happened at energies of around a TeV or so, or 10 TeV, right around where we're probing with the Large Hadron Collider. Prior to that, we really don't know what happens, so that there is a lot of uncertainty. This requires beyond standard model physics, almost certainly. This may well be where this extra dark matter particle formed at some point in this period between grand unification and the electroweak phase transition. Not much is known about the physics at this point, and we're still, and this is one of the goals of particle physics, is to illuminate the physics of this epoch. And then further on, you had quarks condense into hadrons at a temperature of about 10 to the 12th Kelvin, at a temperature of around 10 to the 10 Kelvin, or about 1 second after the Big Bang, between 1 second and 3 minutes, the first nuclei formed. Electrons and positrons annihilated with each other, leaving a small relic abundance of electrons. And then matter radiation equality, the universe transitioned from being radiation dominated to matter domination at about 10 to the 4 Kelvin. At about 10 to the 3 Kelvin, about 380,000 years after the Big Bang, was the epoch of recombination, which we'll talk about in more detail in a minute, and so on and so forth going to today. So this is a basic layout of the standard Big Bang cosmology. And this reminds me of a quote from King Alphonse of Castile, who was a Castilian king in Spain who ruled from 1252 to 1284. Who was a great patron of the sciences, and he funded in particular the formulation of what are now known as the Alphonsine tables, which were the most accurate table of planetary motions, observational table of planetary motions that were available at the time. And in particular, Copernicus is known to have had a copy of the Alphonsine tables in as one of his college textbooks. King Alphonse was reported to have said, referring to the Ptolemaic system, that if the Lord Almighty had consulted me before embarking on creation thus, I should have recommended something simpler. We might say something like that as well about this peculiar mix of matter, radiation, and dark energy that we see in our current universe. We don't know why they come in the proportions that they do, but apparently they do, and we're stuck with it. Much like Alphonse was stuck with the Ptolemaic system in the 13th century. So what's wrong with this picture? Where are the holes in it, right? This all fits together well. It matches observations. You could give many, many talks on how we observationally test this basic picture of the hot Big Bang, but it actually fits data remarkably well. But there are a number of things that it doesn't explain, and fundamentally can't explain because of the Robertson-Walker spacetime. This is where inflation comes in. So let's look at these things that the standard Big Bang cosmology fails to explain in terms of its own initial conditions and how it came into existence. And the important point is that looking out in space is looking back in time, as we discussed, right? So as we look back in time, as we look further and further out in space, we're looking further and further out along our own past light cone. We're seeing further and further back in time until we get to a point where we actually hit the singularity of the Big Bang itself. We're looking so far out in space and so far back in time that no matter what, if we pick any direction on the sky and look out about 40 billion light years, what we would see is the initial singularity itself. And it doesn't matter what direction we look, of course. We could look this way on the sky, or we could look in the opposite direction on the sky, and we would see the same thing. If we looked out 40 billion light years, we would see the moment of the Big Bang itself, this initial singularity. And we can't see any further than that because the universe wouldn't have existed any further than that, right? We're trying to look out past the beginning of the universe. So we can only see back a finite distance in time, which means that we can only see out a finite distance in space. We have a horizon. So one way to see this is to draw our expanding grid of squares instead of a space-time diagram, now just on a spatial diagram. And imagine an observer here who, at the moment of the Big Bang, emits a pulse of light. So this travels outward on a spherical wavefront. By symmetry, you can also see that this is as far out as this observer is capable of seeing. So if the universe is only 1 million years old, the radius of this observer here can't see further out than about 1 million light years. If the universe is 1 second old, then that observer can only see out about 1 light second, and so on. So the manifold as a whole, the universe as a whole, is spatially infinite. So there are observers, other galaxies, for example, that are out here. But this observer can't see this observer because there hasn't been enough time since the beginning of the universe for light to travel from here to there. So now as the universe expands, as time passes and the universe gets bigger, our horizon increases, right? The distance you can see out gets bigger and bigger and bigger because the universe gets older and older and older. And at least in a radiation-dominated universe, it's about a factor of 2 times the age of the universe. So that when the universe is 1 million years old, you can see out about 2 million light years. When the universe is 5 million years old, you can see out about 10 million light years, and so on. And so as time progresses, this observer's horizon, this outer circle of what that observer is capable of seeing, gets bigger and bigger and bigger with time, and you see more and more and more of this infinite space as time goes along. So at least as long as the expansion is decelerating, in the case of a matter radiation-dominated universe, your horizon grows in co-moving coordinates, and you can see more and more of the universe as time goes along. And eventually, the second observer will fall inside the light cone of this first observer, and they'll be causally connected to each other and can communicate. So it's important to remember that just like the horizon on the Earth, this is an observer-dependent phenomenon. Right? So if you think of somebody standing on the surface of the Earth, we can only see out a finite distance because of the curvature of the Earth's surface, right? This is the familiar idea. This is the familiar effect of a horizon on Earth. So we can only see out a certain distance. Someone standing at a different point on the surface of the Earth, likewise, sees themselves at the center of a circular horizon. So in cosmology, these horizons are determined by the age of the universe, but just like 2 observers at different points on the Earth who each see themselves at the center of a circular horizon, 2 cosmological observers will likewise see themselves at the centers of circular horizons as well. So another way to think of this on a space-time diagram then is that the radius of our horizon is the radius of our past light cone projected on the initial singularity of the Big Bang itself. It's easy to see that these 2 things are equivalent to one another. And so our horizon then is just the radius of the sphere, this interior region that lies within our past light cone. That part of the initial singularity that lies within our past light cone defines the volume of our horizon. So why is this a problem in the standard Big Bang cosmology? Well, we can look at it like this too. This is I love this diagram because it's a quantitatively correct diagram of our entire horizon volume. So distances are logarithmic. And so we see basically what we see, even though we live in this infinite homogeneous isotropic universe, there's no special place. It obeys the Copernican principle. Every place is pretty much the same as every other place. What we see is completely different. We see ourselves at the center of a sphere, where the outer boundary of that sphere is the initial singularity, is the Big Bang itself. And we live here at the center, and as we look further and further out in space, we see further and further back in time. So out to the epoch when the earliest galaxies were forming, further on back to the epoch when the first stars formed, further back into the cosmic dark ages before the first stars formed, all the way back. But we can't see all the way back to the Big Bang, of course, because the early universe was hot, and it was hot, ionized, and opaque. So we can see almost all the way back to the initial singularity, but not quite. We can see back to what's called the surface of last scattering, and that we'll define in a minute. This, interestingly, is remarkably reminiscent of the Ptolemaic universe that Alphonse believed in, with the Earth at the center of the universe and the prima mobile, the outer sphere of the Imperium, representing a boundary on the universe itself. So weirdly, by taking a relativistic picture of the universe, we actually come back to something that is in structure very reminiscent of the original Ptolemaic cosmology. Of course, in detail, completely different, and for reasons that are utterly different than the structure of the Ptolemaic cosmology. But these two things look remarkably alike, at least qualitatively, which I think is really kind of neat. So let's talk about this surface of last scattering as far back as we can see, and that's this epoch of recombination. So as we look out in space and back in time, the furthest back we can actually see using light is about 380,000 years after the Big Bang, at this epoch of what's called recombination. What happened at recombination that's special? What happened there is the universe passed through the temperature at which hydrogen and helium are ionized. So earlier than 380,000 years, the universe would have been hot enough that all of the electrons would have been stripped off the atoms. The only elements to be present in the universe at early times were hydrogen and helium. And so all of the electrons would be stripped off at a temperature greater than about 3,000 Kelvin. The primordial plasma would have been ionized, very homogeneous, very high thermal equilibrium, but all of the electrons would have been stripped off the atoms. And that means that the photons that were in thermal equilibrium with the background. So this is a black body, so that the universe is filled with a thermal equilibrium black body spectrum of radiation. These photons would have had a very short scattering length, much, much less than the horizon size of the universe. So the universe would have been opaque, like being inside of a fog or a cloud. As the universe cooled below about 3,000 Kelvin, which happened about 380,000 years after the Big Bang, it went through a phase transition where the electrons would be captured by the nuclei, the hydrogen and helium nuclei in the primordial gas, and the universe would have gone from being ionized to being electrically neutral, and it would have gone from being opaque to being transparent. And all of the photons, all this black body thermal equilibrium radiation that at early times was strongly coupled to the charged particles in the primordial plasma, would decouple. It would cease to scatter off of these neutral atoms and essentially free stream through space on scales comparable to the horizon size of the universe today. And so this relic black body radiation left over after this phase transition is the earliest light we can see in the universe. And it's really the leftover light from the Big Bang itself, from the thermal equilibrium black body radiation in the hot early universe at a temperature of, and this transition happened at a temperature of about 3,000 Kelvin, or at an age of about 380,000 years. So when we look out in space and back in time, we see ourselves at the center of a sphere, but that sphere consists of the surface of last scattering, which is the moment at which the universe went from being opaque to being transparent. So we're looking up, and what we see is essentially like looking up at a bank of clouds. You can't see past the bottom of the clouds. And this is, of course, the very famous Planck measurement of the anisotropy of this cosmic microwave background. This radiation coming to us from the surface of last scattering is redshifted by a factor of 1,100, which is the amount that the scale factor has changed between then and now, right? So the universe has expanded by about a factor of 1,100 since the moment of recombination. And it's in absolutely perfect thermal equilibrium to about 1 part in 100,000. The temperature at any point on the sky is exactly the same as every other temperature, with variations at the microkelvin level, about 1 part in 100,000. And what you're seeing in this picture is an exaggerated representation of these 1 part in 100,000 fluctuations in the temperature of the cosmic microwave background. These are the primordial perturbations. So these things are caused by underdense regions are going to be a little cooler. Overdense regions are going to be a little bit hotter. So regions where the gas is denser is going to be hotter. Regions where the gas is less dense are going to be cooler. And so these hot and cold spots tell you the variation in the density of the primordial plasma at an epoch of about 380,000 years. This tells us a number of things. One is it tells us the universe really was homogeneous and isotropic to an incredibly high degree at early times. Right? This is uniform to 1 part in 100,000, which tells you that the density of material in the universe was the same to about 1 part in 100,000. The temperature was the same. Everything was uniform, perfect thermal equilibrium to incredibly high precision. Well, one of the problems here is we will find that this has no particular, this incredible uniformity at early times in the universe has no particular explanation in the standard Big Bang cosmology. You have to assume it as a boundary condition, which is unsatisfying for reasons that we'll get into in a second, right? So this is the basic picture. This is what we see. This is as far out as we can see as the surface of blast scattering with the cosmic microwave background. So why do we need inflation? How does this picture fall? How does this picture fail, or at least how does it, what does it fail to explain? Let's take a look at this again. Remember, these things, this high degree of uniformity is quite remarkable, right? It's incredibly uniform. And even more so when you think of the causal structure of this, right? So now if we look back on our past light cone, and if we look back to the, so we start here, this is our current universe. And if we look back out along our past light cone, out in space and back in time to the surface of last scattering, when the universe was 380,000 years old, if we look out in one direction, what we see is that if we look out in this direction along our past light cone, we see that the temperature of the cosmic microwave background was exactly 2.7 Kelvin. And if we look out in an opposite direction on the sky, we go back to 380,000 years after the Big Bang, and we see that the temperature in that direction on the sky was also equal to 2.7 Kelvin, at precisely the same, within a part in 100,000. Except if we now look at the size of the observable universe at the time those photons were emitted, how big were their past light cones? The past light cone of one point on the cosmic microwave background and the past light cone of another point on the cosmic microwave background don't overlap, not even close. Those 2 points on the sky do not share a causal past. There is no way for a photon to have traveled from this point to this point in the amount of time that we had since the Big Bang. They were too far apart. So that for all intents and purposes, each of these points lives in separate universes. So that brings up the question, if these two things are causally disconnected from each other, if they never had any causal contact at any point since the Big Bang, how did they end up in absolutely perfect thermal equilibrium? Same density, same temperature, same everything. One way to do it, of course, would be to just assume a boundary condition, say that the universe, we could just assume that it was taken as an initial condition, but that's not very satisfying. We'd like to come up with some dynamical mechanism by which this point here and this point on the opposite side of the sky can come into thermal equilibrium. Another way to think of this is to take a look at, this is just a zoom in on the Planck map of the sky. And what you find is that if you work out how big on the sky the size of the, so if I take some point on the sky where I observe the CMB, I can say how big was the cosmic horizon at the time a photon from that spot was emitted, and how big does it look to us today? And what you find is that the horizon size would have been about 700,000 light years or so, or a little bit less than that actually, because it's the horizon as seen by sound waves rather than light waves that matters in the CMB for technical reasons. So you have basically you have a horizon size that's a few 100,000 light years in radius. And today that on the sky, that looks to be about 1 degree across, about twice the size of the full moon. So if I look at any point on the cosmic microwave background, the observable universe as seen from that point when the CMB was emitted was only subtends about 1 degree on the sky. And so each of these little circles, each of these different spots on the CMB were essentially in completely different universes. They were causally disconnected from one another. Yet all of these spots on the sky are in thermal equilibrium to 1 part in 100,000. And standard Big Bang cosmology doesn't explain this. So how do we come up with an extension to this theory, right? How do we come up with a dynamical way that we can bring all of these points into causal contact in the very early universe? Well, we have to replace that very early evolution of the universe by something else. We have to get rid of that initial singularity and create replace it with some kind of dynamics that can actually bring all of these different places into causal contact, right? So the standard Big Bang cosmology is not incorrect, but it is arguably incomplete because it doesn't explain things like the homogeneity of the cosmic microwave background. The way we do it is by using vacuum energy. Just like the universe today is dominated by a cosmological constant and we are asymptoting in the future into exponential expansion, what we're going to do is assume that very early in the universe, probably around the time of grand unification, although it's model dependent, that the universe was dominated not by matter or radiation, but by some kind of vacuum energy, something that acted like a cosmological constant, which caused the expansion of the universe to accelerate and the universe to expand in a quasi-exponential way. This exponential expansion, or any accelerating expansion, has unique properties of the horizon. Before, remember, I showed you that the horizon grows with time, that an observer sitting in the universe sees more and more and more of the universe as time goes along. In an accelerating universe, exactly the opposite happens. You see less and less and less of the universe. In particular, so now we can take two observers at some early time who are inside each other's horizons, so they're causally connected to one another. And then as the universe expands, because of the accelerating expansion, very rapidly, so in accelerating expansion, the horizon size of the universe remains approximately constant. It's given by the inverse of the Hubble parameter. But the universe is expanding, the space itself is expanding exponentially quickly. So two observers who start out inside each other's horizons are very quickly swept outside of each other's horizons. So another way to think of this is if these two observers were moving at less than the speed of light relative to one another at early times, so they would be causally connected. As the expansion of the universe accelerates, they would eventually be moving away from each other faster than the speed of light, and this observer would be drawn outside the horizon of this observer, and they would no longer be in causal contact. This is nice because this is a good way to explain how these 2 points that we see in the late universe as being out of causal contact. In an accelerating universe, if there was inflation early on, they could have started out inside each other's horizon, causally connected, which means that they could thermally equilibrate. Then this accelerating expansion would pull them outside of each other's horizons, and this expanding space would then become very large relative to the horizon size, but it would maintain that thermal equilibrium. So accelerating expansion immediately gives us an explanation of the thermal equilibrium of the early universe on superhorizon scales, because observers would have started out inside their causally connected, reach thermal equilibrium, and then be stretched out to a causally disconnected scale. You get something else for free there, which is that it also explains why the geometry of the universe, right, why the spatial geometry is so close to flat. We observe that the spatial geometry is flat. It's neither positively nor negatively curved to about 1 part to a fraction of a percent. And inflation explains this neatly, because if the space is expanding faster than your observable universe, then it's just like if we're standing on a sphere and we look at our horizon. If the sphere is big enough, then we can approximate any local patch of that as being flat. So this exponential expansion takes, even if the space starts out with some curvature, the overall space grows to such a size that any local patch of it appears to be very, very close, in fact, exponentially close to geometrically flat. So inflation explains the thermal equilibrium of the early universe, it explains the homogeneity, and it explains the geometric flatness of the universe, all with a single mechanism, which is this accelerating expansion. Drawn on a space-time diagram, it looks like this. It turns out that in the accelerating expansion case, the initial singularity, what we thought was the surface of the Big Bang, this initial singularity at the beginning of the universe, actually isn't the beginning of the universe at all. It's just the end of inflation. So before the onset of the hot Big Bang, you have this period of accelerating expansion, inflation, that's dominated by vacuum energy, in which case the universe would have been very cold, close to absolute zero. it would have been everything but the vacuum energy would be diluted out by the exponential expansion. Remember, matter and radiation, the density goes as 1 over a to the fourth. So if a is increasing exponentially, those get suppressed exponentially quickly. So if inflation gets started somehow, you'd have this period of arbitrarily long period of accelerated expansion before the onset of the hot Big Bang that smooths everything out, makes the universe completely homogeneous, and also makes the universe exponentially close to geometrically flat. So we can, with one mechanism, that is by replacing this initial singularity of the Big Bang with the end of this inflationary period, we can kill multiple birds with one stone, because inflation explains all these different properties, gross properties of the universe, just with one assumption, which is this initial period of accelerating expansion. That's the basic idea of inflationary cosmology. Now, an important thing here is that inflation has to end. So this can't be like Einstein's cosmological constant, because Einstein's cosmological constant has no dynamics, right? If the vacuum of empty space has no dynamics, if the vacuum energy has no dynamics, then the exponential expansion goes on forever. In fact, this inflationary period has to end, and the universe has to somehow transition from this zero temperature vacuum dominated state into a high temperature radiation dominated state at the end of inflation. This process is called reheating. And so you have to add dynamics to this. You have to have something that acts like an energy density of empty space, but actually has dynamics. It changes with time in order to make a successful model of inflation. Luckily, particle physics gives us an ideal candidate for this, which is spontaneous symmetry breaking, which you also may have heard of by way of the Higgs mechanism, which is something that particle physicists stole from condensed matter physicists. It was originally invented to explain superconductivity. And then we cosmologists have come along again and stolen it from particle physics. And to understand spontaneous symmetry breaking, the analogy I like to use is a pencil balanced on its tip. So imagine you have just balance a pencil on its tip, right? What happens to the pencil when you stick it up on its tip? Of course, it falls over. Right? So very rapidly, if I take a pencil and I balance it upright, it'll fall over to its side on a table or something like that. So the important point is, however, that when the pencil is in an unstable equilibrium, classically, if I balance that pencil perfectly, it will stay there forever. Realistically, it won't, because there are air currents, gravity, quantum fluctuations, whatever will always knock it down. It's an unstable equilibrium, but nonetheless, it's an equilibrium point. At that unstable equilibrium, the system possesses a symmetry that if I rotate that pencil about the vertical, nothing changes, right? So this is symmetric with respect to vertical rotations. So I have an unstable equilibrium that possesses a symmetry, in this case, a rotational symmetry. Now, when the pencil falls over, if it falls down to the table, it no longer possesses that rotational symmetry. Right? In particular, now it has to pick out a direction. It has to pick out a direction in which it falls. Because of the symmetry, the direction is arbitrary. It can fall in any direction at once, but once it does, it has picked out a particular direction in the space, and the pencil is no longer rotationally symmetric. We say that symmetry is broken, right? So the pencil, when it falls from the vertical to the horizontal, starts out with a rotational symmetry, and that symmetry is broken by the pencil falling over. The pencil picks out a particular direction in space, and if I rotate it, I don't get the same thing back. It's not symmetric under rotations anymore. So we can plot the potential energy of this thing as a function of the angle of tip, right? So when it's sitting upright like this, it has a lot of potential energy. That potential energy gets converted into kinetic energy as that thing falls over. And then it has a stable equilibrium state, which is laying sideways on the table, that breaks the symmetry and picks out a particular direction in space. So we can draw a potential surface in this way by drawing the potential energy of the pencil as a function of the angle of tip. So as it tips further and further over, the potential energy drops and drops and drops until it reaches a minimum, which is the point at which the pencil is sitting on the table. Notice that this is the potential surface retains the original symmetry of the unstable state, that because of the fact that the potential energy doesn't depend on the direction in which the pencil falls, this thing will have this sombrero shape called a Mexican hat, which is very familiar as the shape of the potential for the Higgs boson. It applies to all kinds of things: the Higgs boson, ferromagnets, any system that goes through a spontaneous phase transition, you have a symmetric stable, you have an unstable symmetric state that possesses a potential energy. You have a stable symmetry breaking state where the potential energy is at a minimum. In this case, in the analogy of the pencil, it would be the pencil sitting sideways on the table. And so in particular, then you have, there's potential energy here. That potential energy disappears when it comes down here. So this is our basic idea. This is our analogy for symmetry breaking, is that we have a symmetric state that possesses potential energy. We have an asymmetric state in which that potential energy is minimized. Except in the case, for example, of like the Higgs boson, this is, of course, the symmetry breaking doesn't pick out a particular direction in physical space. It's in a more abstract space of field theory. But a quantum field like the Higgs boson, in fact, is not just analogous to a single pencil falling over, but in fact, a quantum field permeates all of space. So the Higgs boson permeates the entire universe, and it's and interactions between particles in the Higgs boson are what give them inertia or mass. And so a way to think about of the Higgs boson and the symmetry breaking phase transition associated with a scalar field like the Higgs or any generalization of it is that you put a pencil at every single point in space-time. And each of those pencils in its symmetric state has a small amount of potential energy. And what that means is that basically that potential energy of this field, because it's distributed across all of space, is going to act like a cosmological constant. It's going to act like an energy density of empty space when it's really just the potential energy of this field, which is permeating all of the space, and it's like filling the whole space with a bunch of pencils standing on their tips. And so this potential energy associated with the field acts like a potential energy of space itself and acts like a cosmological constant and drives expansion. The beautiful thing is that this is dynamical now, right? Because of the fact that this is an unstable equilibrium, when the symmetry breaking happens, all the pencils fall over. And in fact, not shown in this diagram, they're actually all coupled to one another so that they all fall in the same direction. When all of the pencils fall over into their symmetric state, this potential energy is minimized, and you no longer have an energy density. You can in fact assign a zero potential to this. There's no longer any vacuum energy in the left of the universe, and inflation comes to an end. So this process of spontaneous symmetry breaking gives us exactly the dynamics we need in order to have an early period of inflationary expansion where we're dominated by vacuum energy, which is just the potential energy associated with the scalar field. And then inflation ends when it goes through the phase transition, when the pencils all fall over and they reach the minimum of their potential energy, and we no longer have vacuum energy and we no longer have accelerating expansion. So to draw this very schematically, we can draw this symmetry breaking potential in one dimension like this. Up here on top of this, we have, as long as it's flat enough on the top, that the field can roll along slowly and inflation lasts for long enough. And in particular, this has to be quite flat in order for inflation to go on long enough to explain the flatness and homogeneity. Then the energy density of the universe is just given by the kinetic energy of the scalar field plus the potential energy of the scalar field. And this V of phi is now just the shape of this potential surface. And so early on, during the inflationary period, this thing is sitting up on this flat portion of this plateau of the potential. The kinetic energy is subdominant, the potential energy is dominant, and so this thing acts just like an energy density of empty space. It acts like a cosmological constant and drives accelerating expansion. As the field evolves along, eventually it rolls down the hill until it gets to a point where the hill is steep enough that we no longer are dominated by potential energy, but in fact the field acquires kinetic energy, right? As that pencil falls over, the potential energy gets turned into kinetic energy. And then this kinetic energy of the field is retained in this thing, so it starts sloshing around the bottom of its potential. And if it's coupled to the other particles in the standard model, for example, or at whatever extension of the standard model you want, as long as it's coupled to the rest of your theory, then this coherent, basically you have a huge Bose-Einstein condensate filling the universe. It's just the energy density of the scalar field. Couplings to other particles will cause that to decay, which will heat the universe up to a thermal equilibrium state, and you have this initial condition for the hot Big Bang, so that the energy that heats the universe and brings on the hot early universe that we see in the Big Bang model comes from the decay of this potential energy that was originally stored in the scalar field and caused the accelerating expansion. That potential energy decays into the particles of the standard model, heats the universe up. That's the period of reheating, and we transition to a hot Big Bang phase of the universe, and everything works really nicely. Right, so this is the basic picture of inflation, is you have an early period of vacuum-dominated expansion, and you have a late period of radiation-dominated expansion that happens after this field. The energy that was contained in this field decays into all the particles of the standard model. So this is the basic picture of the inflationary universe. Right? So it bears mentioning that the shape of the potential surface is not known. It could be something that looks like this, that looks like the potential for the Higgs boson or a pencil falling over. It might be something even simpler that has no symmetry breaking at all, and the system is just displaced from its minimum, and the true vacuum is a symmetric one, and so you could have a potential that was shaped like a bowl. We don't really know precisely what the shape of this potential is, although certain potentials can now be ruled out by data, and hopefully we'll have time to talk about that. Oh my gosh, I've already run out of time. So let me finish up here, actually, by talking about quantum fluctuations. So in particular, this is a classical picture of the universe that I've just described, but in fact, these objects are quantum mechanical. These scalar fields are quantum mechanical objects. So quantum mechanically, they don't just roll down the hill classically, right? Classically, if I have this ball rolling down the hill, the scalar field evolving, it will classically just evolve downward. If I include quantum mechanics, in fact, quantum fluctuations will cause this to jump around a little bit at random. It can actually jump back up the potential as well as jumping back down again. And in fact, it's these quantum fluctuations, these 0-point fluctuations, the quantum fluctuations in the field, that are responsible for the perturbations in the universe. One way to think of it is a pair of virtual particles like Hawking radiation. You're familiar with the idea that in Hawking radiation, you have a pair of particles that pop out near the horizon of the black hole. One of them gets eaten, the other one goes off to infinity, and the universe Hawking radiates. In an inflationary universe, you've got pop out a virtual particle pair. They get swept out of each other's horizons too quickly to recombine. And there's a process that's exactly identical to Hawking radiation that happens at the horizon of the accelerating universe. Another way to think of it is that a short wavelength quantum mode gets stretched out to wavelengths larger than the horizon size exponentially quickly and gets frozen into the background. And this is a quantitative diagram of this that is not so important. And so what you see here is that these quantum fluctuations that start out at short wavelength and get stretched to long wavelength are continuously populated. So if I have a short wavelength fluctuation, it gets stretched outside of the horizon size where it becomes classical and becomes a classical perturbation that's bigger than the horizon size of the universe. A shorter wavelength fluctuation will exit the horizon later, and then later on will fall back into the universe as a classical perturbation. So it's this quantum, this stretching of quantum modes, long wavelength quantum modes earlier and short wavelength quantum modes later, that determines the initial perturbations in the universe. So the cool thing about inflation is that not only does it explain the homogeneity and isotropy and flatness of the universe, it also explains the presence of these 1 part in 100,000 perturbations in the cosmic microwave background. These are actually generated by quantum fluctuations during the inflationary epoch itself. And you can calculate these quantitatively. If I write down a particular form of the symmetry breaking potential, you can work through the math and calculate exactly what the statistical form of these fluctuations in the CMB are and compare them to data, which is an ongoing process, right? So to finish up, I want to talk about the very early period of the universe, where in fact, generically what you find is if you look at these sort of symmetry breaking potentials, you find that very early on in this inflationary expansion, these quantum fluctuations actually dominated over the classical evolution. That the field is rolling so slowly that the field is just as likely to jump up the hill quantum mechanically as it is to jump down. And what you find then is that inflation only ends locally. Globally, over a larger point, inflation keeps going forever. So because of the fact that the field is just as likely to jump up as it is to roll down, it only rolls down to the minimum, and inflation ends in particular regions of this larger inflating space-time. And there's even more regions, and it's since it's exponentially expanding, you're creating new space exponentially quickly. And that expansion wins over the classical evolution. And so the picture you end up with then is that you end up with a multiverse. You end up with inflation ends in little bubbles. Think of an expanding. Think of the multiverse as a glass of beer, where the bubbles in the beer are the field relaxing to its minimum and forming a universe like our own. But in between them is dominated by field still in its unstable state, expanding exponentially quickly. And the inflation is ending over and over again, an infinite number. This expansion goes on an infinite number of times and ends in an infinite number of times and creates an infinite number of these bubbles that are all being stretched away from each other by exponentially faster than the speed of light, and they can never intersect and we can never detect their presence. This is the idea of the inflationary multiverse. And in particular, inside each bubble, you can see that although it appears as a finite spherical region, a little bubble that's expanding at the speed of light from the outside, to an observer inside of it, it actually looks like an infinite universe, because we can take the interior of the bubble, borrow some of the time and turn it into space and actually foliate, so that now we have spatial surfaces that are parallel to the light cone of the bubble, right? So this is the expansion of this bubble that is moving outward at the speed of light. We can redefine space to be along this hyperbolic surface nestled inside this bubble, and time to be perpendicular to it. So now the bubble wall is in the past, and this fine bubble that appears to be finite from the outside contains an infinite universe inside of it. So our infinite space-time lives inside a single one of these bubbles inside this larger infinite multiverse, in which there's an infinite number of these other bubbles as well that would be separate universes that we can never interact with. And this is reminiscent of the Renaissance philosopher Giordano Bruno, who took the Copernican principle so literally, and probably was hundreds of years ahead of his time, that he proposed this idea of an infinity of worlds, that the Earth was not only not unique, but it was one of an infinite number. And he wrote, in 1584, he wrote, "Thus is the excellence of God magnified and the greatness of his kingdom made manifest. He's glorified not in one, but in countless suns, not in a single earth, a single world, but in 1,000,000. I say in an infinity of worlds." And Bruno's infinity of worlds, this Copernican idea that not even our own, essentially our own universe is unique, is beautifully realized in this inflationary multiverse, in which we have not only an infinity of worlds, an infinity of planets, but we have an infinity of universes as well, and we live in but one of them, which is a lovely picture. So I'm going to end there, and I'm sorry I ran a couple minutes over, and thank you for your attention. I'd be happy to take some questions. So how about I unshare my screen, and we can take a few questions.
So if you have a question, please speak up or send a message in the chat and I will read it for you.
Why am I? My screen share, stop share, there we go. Okay. I'd be happy to take some questions. No questions. Is there any direct connection between, would you like to read the questions, Nadine? I'm sorry, you're running this, so I'll let you.
It's okay. Is there any direct connection between quantum vacuum fluctuations and inflation?
Yeah, I mean, that's kind of the point here, is that I went through it a little bit quickly, but the idea here is that these quantum fluctuations, right? So these classical, go back to here, right? So these little quantum fluctuations in the inflaton field, the field is, when that field quantum fluctuates, it goes up or down the potential. That changes the density of the universe, right? If it fluctuates up the potential, the density of the universe is a little bit higher in that region where it's fluctuated upward. If it fluctuates downward, the density is a little less. And so these quantum fluctuations in the inflaton field, this little bit of quantum jitter as it classically rolls down I'm not sharing my screen. screen, so you're not seeing what I'm seeing. Let's do that. So these quantum fluctuations in the field, as it rolls down, are directly connected to the density perturbations. And as these get redshifted outside the horizon, as they get stretched to extremely long wavelengths, those things become classical fluctuations in the density of the background. And this is what creates the density perturbations that we see in the cosmic microwave background. This is super important because it actually connects this idea of inflation, this dynamics that's happening in the incredibly early universe, to observationally accessible data, right? We can see exactly what the form of those primordial perturbations are in the cosmic microwave background. And by measuring those, we can actually measure properties of this potential, how this field was evolving in the very early universe. So this means it's no longer just philosophy. We're no longer just coming up with a just so story to explain why the universe is homogeneous and flat and so on. It makes really definite predictions that we can test. And in fact, it passes the cosmic microwave background looks exactly like you would expect it to from this process of generating density perturbations through quantum fluctuations. So next question.
So the next question is, isn't the standard deviation of the fluctuation stable? What might cause symmetry breaking in the fluctuations?
Well, I mean, I'm not sure precisely what the question is. If you're asking about the statistical properties, yes, it makes the standard deviation in these fluctuations is stable in the sense that they form a Gaussian random field. So one of the predictions of inflation is that these density perturbations should obey perfectly Gaussian statistics with a particular standard deviation. And you can test that. So you can look at the cosmic microwave background, right? Let me bring up this picture of the CMB in particular. So if you look at the CMB itself, you look at the Planck data, right? If you look at these primordial perturbations, and you can measure their statistical properties, right? And these fluctuations in the CMB, it turns out, are precisely consistent with an exactly Gaussian random field, which is exactly what you would expect from perturbations generated by quantum fluctuations during inflation. I'm not sure if that answers your question or not. There's another question.
There's another question. So what do you think about Max Tegmark's mathematical universes?
I don't know. I don't think it's something that's actually testable in any way. So it's interesting philosophy, but I don't think it, at this point at least, rises to the level of physics. There's no way that we can actually do any kind of experiment that would determine whether or not it's true. I mean, inflation certainly predicts the existence of this multiverse, which is rather different than the whole idea of these mathematical universes, right? So Tegmark has a number of different sort of those type 1 multiverses, type 2 and type 3. So just the infinite flat space, but that we can only see a little patch of, that would be what Tegmark calls a type 1 multiverse. The inflationary bubble multiverse would be sort of a type 2. These mathematical universes are sort of type 3 and higher, and they're interesting speculation, but I don't think that they have ever been formulated in a way that can be subject to experimental test or really count as science as of yet. Maybe someday they will, but so far, no. Another question.
Shouldn't be the entropy was increased during the heating process? I think they're asking, if the entropy increased during the reheating process.
Absolutely. That's the whole point of reheating, and you can write it in the language of entropy production, right? So if you think about the inflationary period, right? So the universe is full of a zero temperature, completely homogeneous Bose-Einstein condensate, right? So the temperature of the universe is absolute zero. The entropy of the universe is zero, right? So the entropy in the horizon volume during inflation is absolutely, there's no entropy at all. There's only, there's just this Bose-Einstein condensate, zero temperature, zero entropy. When the field decays in the reheating process, that generates a whole bunch of entropy. And that it generates the initial entropy for the Big Bang itself. right? So that entropy that's contained in the hot gas in the early universe is generated during the reheating process. The universe goes from a zero entropy state to a very high entropy state at the end of inflation. So that's absolutely correct. Any more questions?
I don't see any new questions.
Okay. Well, if there aren't, let me just say thank you very much for inviting me to talk, and I hope you learned something. It was very nice meeting you all.
Thank you for giving this talk. Thank you, everybody who participated, and especially for the questions. And have a nice day.
Have a
Thank
nice
you,
evening,
everybody.
everyone. Bye-bye.
Bye-bye.